Logarithmic graphs are graphs of the form y is equal to log base a of x. And if you remember your logarithms and the way that we can change these around, this is an equation which says that a to the power of y is equal to x, or that x is equal to a to the power of y. And recently we had a look at the graphs of the form y is equal to a to the x, and we can see that these are related. And in fact, you'll study this more next year in Year 12 methods. But when we have graphs where we swap the x and the y, these graphs are called inverse graphs, and they're related graphically as well. So if we have a graph like this, that's y is equal a to the power of x, and we need some arrows and some um, axes and all of that sort of stuff on this graph as well. But when we have graphs like this, inverse graphs like we have here, where we have y is equal to a to the power of x, they're actually just reflected across the line y is equal to x. And so our log graph here, our y equals log a to the x, is a graph which will look like this. And so this is y is equal to log base a of x, and this is the general shape of a log graph. It's flipped, or it's a mirror image of our exponential graph across the line y equals to x. And we can see that more clearly here, where this orange line here is the graph of y equals a to the x. The green is y equals log base a of x. Currently our base is 2 for both instances. And this dotted line is the graph of y equals to x. And you'll see that as I change the values of the base, you'll see that the graphs are a mirror image of themselves. See, they're both getting further and further away from that line y equals x. You'll see that the distances here from here to here, and the distances from here, or this vertical distance across this line here, stays the same all the time. And as I move it around, and even as the base comes back down, you'll see that once again they're mirror images of each other across that line. So this particular exercise is looking at the study of the log graphs, this is the basic shape here. And as with our exponential graph, we have the general form has a y-intercept but no x-intercept. On a log graph, we're going to have an x-intercept here, but there's not going to be any y-intercept, and the y-axis is what we call an asymptote. So exactly how do we get a shape like that? Let's have a look at the graph of y is equal to log base 2 of x. And I'm going to do our standard, let's have a look at some points, but instead of our normal minus 3 to plus 3, I'm going to pick some different points. Now, remembering from our work on logs, the logs that we're going to be dealing with at year 11, x is always going to be positive. We won't be dealing with negative numbers here. So the values I'm going to pick are 1/8, a quarter, a half, and so on. And if you understand your powers of 2, you'll probably see exactly where I'm coming from here. And remembering that I set up here that these are actually just inverses. So if you remember from our index equations, our exponential equations, these were the y values. Well, if we swap x and y, what we see here is that this is going to swap our x and y values here. So remember, log base 2 of 1/8 says what power, 2 to what power here, is equal to 1/8, and obviously here the question mark must equal to -3. So this is -3, this will be -2, -1, anything to the power of 0 is 1, this becomes 1, 2, 3, and this will be 4. So even though x here is increasing quite well, the linear distance between these points is quite small. Our y, the linear distance between our y each here is 1 every time. So from an eighth to a quarter, y travels from -3 to -2 and so on. And then as x gets larger and larger and larger, y is only increasing by 1 every time. And so of course the next one would be 32, would be 5, and 64 would be 6, and so on. And so that is why we get the shape that we do of our log graph, where for very small values of x down here, y increases like so, but then up here, x is getting very large very quickly along here, but y just increases the same 1 each time. So that's why the graph lays down like so. And it never gets exactly flat, it never touches the y-axis down here, and it's a mirror image, as we saw earlier on, of our exponential graph, which looks like that. Obviously, this is the point here, x is 1, y is 0. That's going to be our standard x-intercept. And then obviously at y equals 1, oops, at y equals 1, we're going to get the log base here, which is the point 2, 1. So this green line is currently the graph of y equals log base 2 of x. What happens as we change the base? We'll see as we change the base that the graph changes its shape. We don't have a log base 1 because 1 to the power of anything is still 1, and then the graph also, when it's fractional, the graph flips around the other way. We saw this before with our exponential graphs, a similar sort of effect. As our base gets larger, though, the graph gets quite a little bit flatter because it requires a larger and larger increase of x to affect a single point increase in y. And also remember that we can't have negative bases in our logs. So 0 is undefined, it's not a log anymore. So a has to be a value of some sort, and that's what happens as we change the base. As with our index equations, most of the transformations I'll do will be with base 2.